I will give you a brief summary. So these phase change materials are materials that can exist at room temperature, both in the crystalline and in the amorphous state, which is illustrated up here. And they can be non-volatilely switched between these phases, so from the amorphous to the crystalline and back to the amorphous. And the interesting property they have for like photonic application is that they exhibit huge dielectric contrast between these two states. And first up, why do we actually need these materials? So we want to work with metasurfaces, and metasurfaces in general are like periodic arrangement of nanostructures, as you can, for example, see here. And with that, you can create, for example, manipulation of light, and you can achieve anomalous reflection or even beam steering capabilities that can go beyond conventional optics. And I also brought you an example of a planar lens here. So such a lens would be much smaller than in conventional optics, which is usually very bulky. And especially if you think of infrared optics, which is usually very bulky, this could be a way to replace this. However, these metasurfaces rely heavily on the fabrication, so they are fixed in functionality and frequency once they are fabricated. And this is why people came up with the idea to make these metasurfaces, or with the idea for switchable metasurfaces. And this was pioneered by the Chin-Ludev group in 2010. So they took an ordinary metasurface and deposited one of these phase change materials on top, in this case here the GLS layer. And then they switched it from the amorphous to the crystalline phase and could alter the working frequency by 160 nanometer by simply going from amorphous to the crystalline. And again, in the Chin-Ludev group showed that it's also possible to directly write these phase change materials and use them as metasurfaces by the direct writing of dielectric structures, or writing here. And then they read it out at the same frequency. However, this was then also limited to only dielectric structures, and they could not go for sub-wavelength resonators. And in the same year, our group came up with the idea of placing a phase change material, which is shown here, it's GST, on top of quartz, and was then switched with a nanosecond visible light laser to crystallize the material. And then we probed it with a SNOM. And you can see here the AFM image, and we can already see this nicely, the V-shape here. And this is due to a density change. If you go from amorphous to crystalline, you have a density change of about 7%. And if you then look at the optical image, of course, outside of the Reststrahlenband of quartz, you can see that we have a purely dielectric contrast here. Here, and if we then go into the Reststrahlenband, we can see that the contrast completely changes. And then you see, if you look closely here to the edge, or probably in the zoom in here, you see these nicely confined surface phonon polaritons. And with this trick, we could achieve a confinement of up to a factor of 70. And with this capability of confining the surface phonon polaritons, it was then we deposited a GST film on top of a polar crystal and then switched it again to the crystalline state by simply heating it, and then shot amorphizing pulses in the surface. And again, you see in the topography, it's hard to differentiate between crystalline and amorphous, but if you look at the SNOM amplitude, you see again we have two contrast channels. One is you get the dielectric response here, so amorphous crystalline contrast, and if we now go into the Reststrahlenband, we very well see these high fields of the surface phonon polaritons. And if we then alter the frequency, we see that we can also change this, the mode that is actually inside of this resonator. And now I talked a lot about these phase change materials. I will give a brief further introduction. So this is actually a rather well-known class of materials. So some time ago they were used for DVDs and CDs. Today it's more like storage class memory, like ReRAMs, or even in neuromorphic, or they are a candidate for neuromorphic computing. And now the question is, how can this be used for metamaterials? So essentially, they have the reflectance in the amorphous phase is low, and if you go through crystalline phase, it increases, and if you switch it back to the amorphous phase, it goes then back to the, you get a low reflectance, and the resistant behaves exactly opposite, and this is what is used, for example, in these storage systems. And these materials, they have some remarkable properties. For example, the two phases are stable for more than 10 years, so you can use your CD still after 10 years. They are non-volatile, and you can switch them over many, many cycles. And some of them, especially the material class of consisting of germanium, antimony, and telluride, they show a unique bonding mechanism, which Julian also briefly introduced before. And before we get how to, or I will now show you a brief introduction how we use them for switching the resonance. And just think of the most simplest nanophotonic structure. This is a linear antenna. And by placing this antenna on a substrate, the surrounding also plays a role in the resonance condition of this antenna. And if we look at the formula, we see that this depends highly on the refractive index. So if we increase this refractive index of the surrounding, we can also achieve a red shift in the resonance, or if we decrease it, a blue shift. And this concept can be used on many surfaces, for example, in many applications, for example, on plasmonic, phononic, and dielectric antennas. Can be used for large area switching, or even single antennas can be addressed. And the switching can be achieved thermal, optically, and electrically. And the ones I showed here in red, these are the ones I'm going to talk about. But first up, a brief repetition of the phase change material GST326. Here's like the full dielectric function from the infrared to the visible. And the solid line in red is the crystalline, the real part of the permittivity for the crystalline GST, and the black one for the amorphous GST. And we focus here especially on this mid-infrared region, where we are between the onset of this interband transition and the Trude response, which Julian talked about before. And here we see we have a huge contrast in the permittivity in the real part and very negligible losses in both phases. So this makes it a very interesting material. And now, you may ask, how can we now change the refractive index? And this is, so the simplest way of doing this is we have a metasurface, put the PCM on top, and then we anneal it over the crystallization temperature for a certain time. And then it crystallizes, the refractive index shifts, and we see here a red shift in the reflectance. If we do this now, for example, with the femtosecond laser, we can also address the arrays. This is with a high power femtosecond laser, and switch it already kind of locally. But what we are currently really doing is we try to optically address these antennas individually, and this means that we program each meta atom in this metasurface, and this allows us to fully control, or almost fully control, the amplitude and the phase of these of the light. And this concept was applied to several types of metasurfaces. For example, here to plasmonic nano antennas by changing the surrounding refractive index of the individual meta-atoms. Then we did this also with dielectric antennas together with a group of Hatice Altuk and Andreas Tittel, who is also here. And there we showed that it's possible to achieve 80% of a full 2-pi phase shift. And, but today I want to talk about the directly laser writing of plasmonic structures, and this is done with a new phase change material. It's called IST, it's indium-3, antimony-2, tellurium, antimony-1, tellurium-2, and it has really remarkable properties because, for example, it can be switched between a metallic and a dielectric phase. This is also known for other phase change materials, for example, germanium GST225. However, this happens in these materials only in the visible range, and this is accompanied by very high losses, as you see, for example, here. But this IST material is very different because it has a Trude-like dielectric metallic response in the crystalline phase, and in the amorphous phase, it's a pure dielectric with a similar permittivity like amorphous GST, but upon switching it turns metallic. And this is the perfect material to actually simply write plasmonic structures into the film. And my colleague did this last year. And essentially, you take a layer stack consisting of this calcium fluoride substrate, deposit a thin film of this IST material on top, and then cap it to avoid oxidation because this material tends to oxidize. And then you do the laser writing. You see an illustration up here from the crystalline to the amorphous, and you can also rewrite it. In the light microscope, we see a very tiny contrast. In the AFM, you again see the dark, the crystallines as lower in the topography compared to the amorphous. region. This is again to the density change. And if we now look with the SNOM at it, we can really nicely see how this resembles this asymmetric pattern we usually expect from a metallic resonator. And by writing and erasing this, the resonance here could be appeared and could be and disappeared upon erasing it. And this can be done over several switching cycles, and this is the principle for or it's a basic for optical programming. And this can, for example, also be applied on pre-patterned metallic metasurfaces. So you see here two gold antennas which are very close together, and then an IST patch is placed right between them. And upon crystallization of this IST, the two antennae become one. And in the AFM, it's hard to say is it crystalline or not. But if you look at the SNOM, you see really here where this patch is placed, you see that this is really has the same contrast as on the gold. So we really have there a connection. And this also can be measured in the far field. So the relative transmittance changes between the amorphous phase of the IST and the crystalline phase over several hundred nanometers. And what else can be done with this? So we can actually now write antennas, and these antennas can be or can be modified. So for example, we take this antenna, it's rather short. We then crystallize it or add an additional crystallizing pulse. This leads to a shift in the resonance because we elongate the antenna. And the interesting principle is here, usually if you want to tune such a metasurface, you try to change this refractive index here, n. But this is more difficult than simply changing the length of the antenna. So we now simply change the length of the antenna. And this works in one way by crystallizing, by elongating the antenna, and then we shorten it by amorphizing pulses. And if we completely remove the antenna, this resonance disappears. And this can also be applied, for example, to dividing the antennas, and also more complex structures can be written. For example, here, some type of split ring resonators by combining amorphizing pulses in gray with an by combining a crystalline pulses with one amorphizing pulse, then we can get these split rings. And this is what we looked at recently. So we tuned the magnetic resonance. So far, I only showed dielectric resonances, and we can tune this magnetic resonance by creating such split ring resonators. And then we change the length, the arm length of these resonators. And the shorter the arm length, the shorter the resonance wavelength. And this is shown here as an illustration. And if we go to the experiment and the simulation, we clearly see the electric dipole stays roughly at the same position. And here we just have IST patches, so just an electric dipole. And if we go to the split rings, we really see how we can shift the resonance in dependence of the arm length to the shorter wavelength. And then if we recrystallize it, this fully disappears. And this agrees nicely with the simulation. And there we use the SNOM to actually try to assign the modes. So for these IST patches here, we looked with the Stuttgart Instruments laser, which was already introduced by several groups, at 4.4 micrometers below a 70 nanometer capping. So we have a comparably short wavelength, but still we can look through 70 nanometers capping. You see the AFM image here. You see the optical amplitude image here and the phase image here. And now you might say, oh, this is just a material contrast. But if you look very closely, you see here the dark spot and here the bright spot, and similarly in the phase, and this indicates that this is somehow a mixture of the material contrast and the electric field. And if we now go into the magnetic resonance, so here at 10.6 micrometer with an ordinary CO2 laser, again, the amplitude image is not that interesting, but in the phase we can clearly assemble a pattern. We have opposite phases here, and if you look closely here and also here. And this might indicate that we have an electric and a magnetic dipole mode. However, to get there a final conclusion from this, further modeling needs to be done, because we also have this huge material contrast. Yeah, and in summary, this IST can be used for nanophotonics, so by simply switching between the crystalline and the amorphous phase and the metallic and the dielectric phase. This can also be used for resonance tuning or nanoscale soldering and magnetic dipole tuning. And in general, SNOM can be applied to PCM nanophotonics. On the one hand, to determine the material contrast, so dielectric contrast between the crystalline and the amorphous phase, or to map the charge carrier concentration as presented by Julian, or to map even defects. And the optical near fields are, for example, can be used to, that a SNOM can be used to map the field distribution, mode assignment, or even the polariton imaging, which we recently saw. And currently we have ongoing studies, for example, to study the crystallization behavior of certain materials. So for example, to look for nuclei in such a structure here, in such an IST ring. And this shows you, this is the corresponding amplitude image, and it shows impressively that we can really learn something from the SNOM image about the crystallization behavior of these materials, since this was not shot with a crystalline amorphizing pulse, but two crystalline pulses with different power. Yeah, and probably as a short outlook, we also started to look at topological metasurfaces in collaboration with a group of Professor Zehngraf. And here we had lattice, or more or less a photonic crystal made out of silicon.
So I think we have to close out here. So
it's the last slide.
Yeah. Okay.
Okay. So and then in this photonic crystal, we introduced a small pillar, and if you map the modes that can be inside this photonic crystal, you see you have solutions here, and one right inside the band gap. And this one is topologically protected. And this is what we also observed in the SNOM when we looked at it at 100 terahertz, so close to 3,000 nanometers. And this agrees very well with the EZ field in the simulation. Yeah, and this brings me to the end. Here are the acknowledgements. So thanks to my colleagues and also the collaboration partners I presented here.
Right.